All right, so we got our unit exam review here. Now we've been in this unit for just over a month. All right, it's the longest one. Okay, it's even longer than chemistry. Part of that is individual choice on your teacher's part. If you had Mr. Van Erf's class, he'd have spent more time in biology because, well, he's a biology guy. It's not his fault. He's just a biology guy. Okay, I'm a physics guy, so I spend more time in physics. Okay, and when the chem teachers teach it, they spend more time in chem. Okay, so the end is you still got taught all the same stuff, but I give you a little more enrichment in the areas I'm more familiar with. They give you more enrichment in the areas they're more familiar with. Okay, so it's a long unit. That means that there's a lot of stuff you need to cover. This unit is more like chemistry, however, in that it is much more skill-based. So you need to demonstrate your ability to do things on this exam more so than you did on the biology exam, where you had to remember stuff. Okay, you had to remember and apply. This is going to be demonstrate and apply. Right. So there's a lot more of the problem solving in this one rather than like labeling and stuff like that. Okay, so that's something to keep in mind, because that means for you in terms of studying that you need to spend more time doing practice problems than you do reading over your notes. Okay, I mean, not to say that you shouldn't read over your notes, absolutely you should. Okay, but there's obviously less notes to read over in this unit than there was in biology, where it was basically all based on your notes. All right, so first thing we covered in this unit was the types and forms of energy. That's going to be tested in the multiple choice because it's pretty much all recall. All right, so I asked you what kind of energy would be possessed by wind. Okay, you would probably say something like, in a multiple choice question, I put like chemical, mechanical, light, sound, or something. I don't know, whatever. It'd be a multiple choice question. Okay, probably the most correct answer on that one would be mechanical. Okay, because it's moving air. Okay, it's moving matter. Okay, if it's moving, it has mechanical energy. Okay, sound would be a byproduct of wind. Everyone kind of follow me on that? Okay. So in that types of energy, okay, there's not going to be much on the people. Like, yeah, we had, like Rumford and Joule and Newcomb and those kind of guys. Like, there's not going to be much on them. If there is anything on them, it's going to be pretty obvious who I'm talking about, okay, in a particular question. Okay, you also need to know the 3 types of systems. Okay, that was one of the things we covered the first day. The 3 types of systems were open, closed, and isolated. Open, closed, and isolated systems are different in the way in which they interact with their environment or with their surroundings. Okay, just as a quick review, an open system can exchange both matter and energy with its surroundings. A closed system can only exchange energy. An isolated system exchanges neither one. Okay, so just remember those again, multiple choice kind of question. And then the laws of thermodynamics. Okay, first law of thermodynamics is the law of conservation of energy. Okay, energy can't be created or destroyed, but you can change it by doing work, okay, or transferring heat. And then the second law of thermodynamics is about the direction of energy transfer. It always goes from hot to cold, high to low, okay, whichever. Okay, and there's maybe a couple of multiple choice questions, about thermodynamics, how heat engines or heat pumps work. Okay, so like a jet engine is a heat engine. It uses the second law of thermodynamics to produce thrust. Okay, by having a very hot area near a very cold area, that flow of heat from one place to another takes matter with it and then can be turned into mechanical energy. With a heat pump, okay, what was an example of a heat pump we talked about? What's that? A fridge, yeah, fridge or an air conditioner, because they're actually using energy to push heat into a hotter area against the second law of thermodynamics. The analogy we used was it's like active transport for heat. Okay, it's pumping it against the direction it would naturally go. All right, so know about those things, heat engines, heat pumps. Okay, also maybe know about perpetual motion machines and why they can't, let's say, exist / do anything useful. There could be a written response item about that because it allows you to apply your knowledge of thermodynamics. Incidentally, why would a perpetual motion machine, even if it could exist, be useless? Yeah, it couldn't ever do anything. Okay, I couldn't make it do any work because what's work? A transfer of energy. If it transferred energy away, it would stop because it doesn't have a source of energy. Okay, remember, you can't get something for nothing, right? So this is having a question about perpetual motion machines allows you to apply your knowledge of both, or show me that you can apply your knowledge of thermodynamics, work energy theorem, conservation of energy in something other than a problem-solving manner, right? So that would be something to kind of watch for. Okay, then we talked about scalar and vector quantities. Is it important for you to know which things we've gone over are scalar and which things are vector? Yes, and not because there'd be a multiple choice question, which of the following is a scalar quantity. Not that that's outside the realm of possibility, but what's more important is I give you a question that has you doing some problem solving, and at the end asks you to calculate the final velocity. If you don't write a direction on that, do you get it right? Nope, because velocity is a vector quantity. Okay, that's where people get burned on scalar and vector quantities, is forgetting in a problem-solving question that what they solved for was a vector quantity and that it had to have a direction. And I mean, our direction stuff has all been pretty simple. It's either been positive or negative, forward or backward. Okay? So you just have to make sure you read the question carefully. Okay, what I often do is I'll write down beside the givens, okay, you know, positive equals forward or east or whatever, just so that I remember at the end that I have to put a vector on my answer. All right, so with the scalar and vector quantities, okay, speed and velocity, okay, so speed is a scalar quantity. It just tells us how fast we're going. Velocity tells us our change in displacement over time. Okay, distance, scalar or vector? Scalar. Displacement, vector. Time, scalar or vector? Okay, acceleration, scalar or vector? Vector, has to be, right? Because you could speed up or slow down. Those are two different directions. Okay, so time and acceleration, all right? Force is also a vector quantity, although it's not going to be super important for what we do. Energy is scalar, again, not super important for what we do, but again, just so that you're aware. Okay, that same day we got our first formula for the unit, okay, and that was V equals D over T, and its counterpart, V equals D over T. All right, but obviously one had to do with the scalar quantities and one had to do with the vector quantities, okay? This one here is speed equals distance over time, whereas this one is displacement over time, and this obviously is velocity. Okay, so remember, if it has a little arrow over top of it, it's a vector quantity. Okay, so could you expect to have some V equals D over T problem solving on the exam? Yep, but probably in the multiple choice. It's not a difficult calculation for you to do. I'm not going to burn a 5-mark written response problem on a V equals D over T question. Okay, so just know that. However, V equals D over T could be part of a position versus time graph question. Sometimes we have to use it there. So know that it'll probably come up somewhere else. Okay, graphing. Graphing's big on this test because we went over 2 different kinds of graphs. We did 2 labs to do with graphing. Okay. Other than work energy theorem and conservation of energy, graphing is the second most weighted item on the test. All right. There are some graphing questions in the multiple choice, okay, where it would be either a simple calculation or a simple interpretation of the graph. Okay, like I show you a picture of a position versus time graph, and I ask you, based on the shape of this graph, what is happening? Okay, so you're interpreting the graph. Or I ask you to do a simple calculation like what's the velocity of the object on this position time graph or something like that. Okay, in the written response, there could be also some interpretation stuff, but I guarantee you there are questions about calculations to do with both kinds of graphs. Okay, there's a position versus time graph in the written and a velocity versus time graph in the written. I am going to ask you to do exactly the same things I asked you to do on your graphing lab and your need for speed lab. Okay, I'm going to ask you to do exactly the same things. All right, so that's going to mean use y equals mx plus b, okay, to calculate slope or to extrapolate from beyond the graph or something along those lines. Okay, I'm going to ask you to calculate the displacement by finding the area under the line on the velocity time graph. All the things we did in class, I'm going to ask you to do. Right, so you got lots of examples of us doing those things. Okay, there's podcasts you can watch where I went over all the different graphs on that worksheet. It's going to be stuff just like that. Okay, I'm not going to surprise you. There's nothing I can ask you to do on those graphs we haven't done lots of times, but no, I'm going to ask you to do every one of the things you had to do in class. Okay. All right, so with graphing, okay, if we have a position, you know what, this is just a mess. I'm going to erase it and draw it again. All right, I got a position versus time graph that looks like that. That's supposed to be a straight line, by the way. It doesn't have a curve in it. And I give you this. Like I actually give you the numbers, not just the equation. And I have it here, just like it would look in Google Sheets. Okay, if I ask you in the questions, using your graph, calculate the following. Okay, should you use the graph to calculate it? Yes. Okay, that means use the equation on the graph. Don't use a data table. Okay, don't try to read points. Okay, use the equation of the line to help you calculate things. If a question is out of 1 mark, how much calculating is there? None. Okay, if it's only out of 1 mark, the answer's right in front of you somewhere. All right, everybody with me on that? Okay, if it's only out of 1 mark, don't show me 5 marks worth of work. You're definitely doing it wrong if you do it that way. Okay, and I tell people this every single time, yet it continues to happen. If a question is out of 1 mark, the answer's right there. You just have to find it. Okay, it doesn't require any calculating. Okay, but I see people do that, and it kills you, not so much in marks, it kills you on time. How long should a 1 mark question take you? Yeah, like 10 seconds. If it's 1 mark, it's recognition. It's right in front of you. If you do 5 marks worth of work, how long did you spend on a 10-second question? 5 or 6 minutes maybe? Okay, is that going to help you finish the test on time? Okay, this is not like for this test specifically, this is tests in general. That's test management. Okay, look at what a question is out of. There's a reason why we put the marks after a question, so you know how much time you should be spending on that. Okay, that's why we don't like the format of the diploma exams. Okay, they're all multiple choice. So a question that could take you 20 minutes is only worth 1 mark. Okay, we don't think that's fair. Right? In this way, okay, with this written response, you know that's a 5-mark question. I got some work to do. That's a 1-mark question. I just have to find the answer. Okay, and it helps you to manage your time on a test. Everybody with me there? Okay. All right. So on a position versus time graph, if I'm looking at y equals mx plus b, what does m stand for? Slope. What does it stand for on this graph? What does it represent? Not acceleration. Okay. If I manipulate for m, It'll be y minus b over x, which will be one position minus another position divided by, what's on the x-axis? Time. What does that calculate? Ooh. You guys have some work to do over the next few days. If no one can answer this question, I just got this sinking feeling in the pit of my stomach. It's velocity, average velocity. Okay, that's the slope of the line. It's final position minus initial position, which is displacement divided by time. Okay, if the question, okay, on the test, you would get it, it would look like this, I might ask you, calculate the position of the object after 5 seconds. Okay, if that wasn't on the graph, and you'd have to manipulate that for, okay. I would suggest over the weekend watching some podcasts on graphing, because right now you guys are giving me blank looks you shouldn't be giving me. Okay, this is stuff we spent a lot of time on in class. Guys, what's on the y-axis of this graph? Position. Okay, what's on the x-axis of this graph? Okay, so if a question asks you calculate the position after this much time, you're solving for a what value? A y value, right? Position is on the y-axis, so you're solving for a y value. If it asks you how long does it take to reach a position of 10 meters, you're solving for an x value, because time is on the x-axis. Okay, I'm so worried right now, okay, that you guys don't know this stuff. Okay. Okay, if we're looking at a velocity versus time graph. All right, on your Need for Speed lab, your graph had exactly that shape. And I asked you to calculate the displacement. Okay, what did you do to calculate the displacement? Right, we found the area underneath the line, okay, because that represented essentially taking the average velocity and multiplying by time. Okay, what does the slope of this line represent? It represents acceleration. It's the change in velocity. Okay, and remember, if we manipulate this graph this way, it's not final position minus initial position, it's final velocity minus initial velocity over time, which is acceleration, which is the slope of the line on this graph. Okay, so if you get a question like this and it asks you, how long would it take to reach a speed of or a velocity of 200 meters per second? You'd be solving for n what value? How long would it take to reach x? Okay. All right, I would suggest doing some practicing on that over the weekend. And by suggest, I mean do it, damn it. Okay, sounds like you need some practice. Okay. All right. Did I mention there's lots of graphing? There's lots of graphing. Okay. Then we talked about acceleration. Okay, and we looked at, the problem solving to do with A equals VF minus VI over T. What was what? 4 was graphing. Or sorry, 3 was graphing. Did I skip a number? I don't know. I skipped a number somewhere. The next thing is acceleration. So there could be some multiple choice questions about what acceleration is. After all, we had a lab kind of about that. And then there could be some simple problem solving in the multiple choice and some more in-depth problem solving in the written. So expect an acceleration problem very similar to the ones that were on your worksheet in the written response. Okay, and then we got into the energy part of the unit, which I said is the most mark dense part of the exam. Right, so we talked about how work is force times distance. We talked about how work is a change in energy. There'll certainly be some multiple choice questions checking your understanding of that. But more importantly, there are many problems in the written about work energy theorem. Okay, that being work is a change in kinetic energy, work is a change in potential energy. Essentially, there's one of each, and they're just like the ones we did on our quizzes. Okay? Like this morning, we had that one about how much work is done in carrying something from 10 meters to 35 meters. Okay, it wouldn't be that simple. That might be okay, like a multiple choice kind of one. This one would ask, something about what force would be involved or how far would it have to be taken or whatever. Okay, so you'll have definitely some work energy theorem questions. Okay, 2 of them. Okay, for sure. Make sure you go over those, but it looks like you guys know how to do those. Okay, and after work energy theorem, then we talked about conservation of energy. You guys seem to get that as well. So EI equals EF. Okay, roller coasters, toboggans, bobsleds, whatever. People jumping out of planes without parachutes. Okay, really morbid things. Okay, where energy is conserved. And then there's the one thing we haven't talked about in detail yet, which is what I'm going to go over tomorrow, and that's efficiency. Okay, it's a review for you guys, so I'm just going to talk about it tomorrow in the short class on Friday. Okay, where work in divided by, work out divided by work in will give us our efficiency. Okay, so that's what's on there. Now, give you a little more detail as to how many questions and stuff here. Work out, W-O-U-T, and then divided by work in. Okay, so there are 20 multiple choice questions, so significantly less multiple choice than your first 2 tests. And there are 45 marks in the written. So there are 7 written response items. Okay, many of them have an A and a B and a C. Okay, so in the multiple choice, things that are being covered. Okay, like what is, definitions. So like what's work, what's energy. Okay, we talked about how you could have, wind would be an example of what kind of energy or something like that. Thermodynamics, laws of thermodynamics we said are in there. Okay, the types of systems, again, the laws of thermodynamics, heat engines and heat pumps, and then some simple vector scalar stuff, some simple V equals D over T stuff in the multiple choice, some simple graphing stuff in the multiple choice, some simple acceleration stuff, recall definitions, right? A couple of understanding questions about acceleration and a couple of understanding questions about energy. Okay. In the written response, start out with a position versus time graph. Okay, there's 3 questions to do with the position time graph. Now, when you look at a position versus time graph, okay, let's say that you get a position time graph, and because of the scale, it looks like it almost goes through the origin. Almost. How do you know if it really does or not? Check your calculations, or maybe it gives you the equation, right? So like 3.56 x plus 0.045 or something like that. So does it go through the origin? No, it just misses it. Those are important things because they can make a difference in your answer. If you forget, if you just like do all your calculations as though b was 0, you're not going to get the right answers. Okay, so make sure you look at the equation. Okay, as I was saying to you before, using the equation to the line is going to be important. Okay. All right. And then we got an acceleration question. Then we have a velocity versus time graph. And there are 3 questions to do with that. What things did I ask you to calculate from velocity versus time graphs in class? Acceleration and displacement. Okay. Then we got our 2 work energy theorem problems. Then a conservation of energy problem. And then an acceleration problem that will challenge you. Yes, efficiency is just in the multiple choice. An acceleration problem that will challenge you. All right, so the whole test is out of 65 marks, which actually makes it one of the shorter tests that you have written. Okay, but that's because there's a lot of calculating and stuff to do in the written response. Didn't want to make it too long, okay, so that people would finish. Now, on the note of finishing the test, okay, I will be here by hopefully between 10 after and a quarter after 8. Okay? If you want to start early, I will let people start at 20 after 8, or maybe a quarter after if I've got stuff set up. Okay, so if you want to start early, make arrangements to get here early on Monday. Okay, if you normally take the bus, okay, I mean, sometimes the buses only get here at like 8:25, or whatever. Okay, maybe make an alternate arrangement to find another way here so that you can start early. Right, I'll let you right into break a tiny bit, but not much. Okay. All right. Questions from you guys? What are some things you want me to go over? Questions you would like to ask? Graphing, I was going to do it anyway, but I'm glad someone asked. Okay. All right, with our graphing, so let's say that this is a position versus time graph. All right, what's this object doing? Okay, moving forwards, okay? We're almost there. Moving forwards, how are they moving forwards? At a constant, okay, rate. What would be a better word than rate? Velocity, right, okay. So that's like, if this was a question about you telling me what's going on in the graph, moving would get you like 1 mark, okay? Moving forwards, 2, moving forwards at a constant velocity, 3, okay? It's level of detail. It's showing me I understand for sure what's going on here versus I took a wild stab and said it was going, okay? We want to be specific. All right. What's the velocity of this object? Fast will not get you any marks. 3.56 what? Meters per second. How'd you know that? Because it's on there, right? Because we remembered that on a graph of position versus time, solving for m means taking the final position minus the initial position over time. Okay, that is y minus b over x. Okay, that solves for slope. The slope is velocity because it is meters divided by, what's on the x-axis? Seconds. Okay, meters per second. That's, you guys, you don't want to memorize. Okay, you want to work this out. Okay, each time you encounter a new graph, this is what you want to do. Okay, what's my slope represent? Okay, so I took my y values. Y values are in meters. X values are in seconds. Meters divided by seconds is meters per second. That's velocity. Okay, that's what you want to do. If you try and memorize it, you're going to confuse something. Work it out each time, and you're not going to confuse anything. All right. If this was a velocity versus time graph instead, now when I do that calculation, what am I calculating? I'm calculating acceleration because now y values are velocities. And I'm going VF minus VI over t. Okay, so now it calculates something different. All right. If I asked you to calculate how far this thing is going to go after a certain number of seconds, okay, you'd be solving for what? You'd be solving for a y value because meters measures how far something goes. right? That's the analysis that you need to make when you're answering a question like this. You don't need to memorize it, okay? I look at this and say, okay, oh, sorry, this, I changed it back. It's supposed to be meters now, okay? How far is this object going? Then I would calculate a y value. If it was a, now I ask you to calculate how far it would go after X number of seconds, what are you gonna do? Because now it's a velocity versus time graph. Nope, slope tells me acceleration. And I already know the slope. Area under the line. Okay, because what I need to know is, okay, how far did it go? Because it was starting at this velocity, how far did it go after however many seconds I gave you? And then, how far did it go while it was accelerating? Okay, that's the triangle on top. Okay, those are the things we have to remember. So, like I say, it's just a matter of practicing those, reviewing those, maybe watching a couple of podcasts of those being done, okay, so that you remember how that works. But especially look at your need for speed lab. Okay, because you were asked to do exactly that on your need for speed lab. Okay, the question on the velocity versus time graph on your exam is more like the ones we did in class, because the one on your velocity time graph, or sorry, the one on your need for speed lab looked like this. Your velocity time graph on the test has multiple sections. Okay, it's not a single line. Holy smoke, I'm giving you way too much detail on your test. Okay, all right, what else? Okay, I posted your exam review package last week. It's on Google Classroom. I would suggest having a look at it. The last two questions have graphs in them. You don't have to do it in order. Maybe you'll want to look at those first. Okay. There's some energy questions, some acceleration questions. The answers to all the problems are on there in bold. Okay, so you can check and see if you did them right. If it's stuff from your notes, then obviously the answers are on there. You'll have to just look them up. Okay. But all of that stuff is in the review package, which I'll put up on the board here. And you guys can work on that. And if questions come up, ask, and we'll go through them together. Okay, so your unit exam review package starts out kind of with a typed version of what I had scrawled on the board. Okay, so basically your key points and stuff, telling you what kind of things you're going to have to be able to do. All right, and then there's some review problems and activities. So it talks about, giving a definition of scalars and vectors. Okay, examples of technologies using those energy forms. These three people here are probably important. Okay. Mechanical energy and heat, okay, different types of systems, basically all the stuff that I had on there already. And then starting on question 9, there's problems to solve. Actually, I think the answer for number 9 is wrong. I'm just going to double check that and make sure that I've done it right on the one I gave you. So this is an old version, I think. Okay, but it keeps going, guys. There's lots and lots of practice problems on there. There's a conservation of energy one. There's 2 graphs there at the bottom. Right, all kinds of good stuff for you to have a look at. All right, it's number 9 I was going to check, right?